looking at these practice questions then for mock paper 1. Question 1. So this is a question about atomic structure, and we can see in the diagram the model proposed by Rutherford to show the structure of the atom. So pause and read the question. Okay, so we need to think about two features of the current model. So two features, feature 1 and feature 2 of the current model that are not shown in the Rutherford model. Okay, so what we can see is, if we have a look at the particles, we've got a positive nucleus and a negative electron. So first of all, we've just got a positive nucleus. The current model has protons and neutrons are present in the nucleus. And this is not shown in the Rutherford model. Okay, and then the second model only shows 3 electrons in a single energy level, whereas the current model, electrons are found in orbitals at different energy levels. Whereas the Rutherford model does not show orbitals or energy levels. So this could easily have come from a GCSE paper. It's a really straightforward question, but where you could potentially become unstuck here is just a lack of being specific. So make sure when you're answering questions like this, you write in a full sentence which makes it really clear the features that you are stating are in the current model and the features that are not therefore present in the Rutherford model, just to make sure that you are absolutely answering the question, because you know this, it's straightforward. So don't lose marks by being unclear about exactly what you're referring to as being present in each model. So part B then, a sample of tin is analysed in a time-of-flight mass spectrometer. This sample is ionised by electron impact to form 1+ ions. A table below shows data about the 4 peaks in this spectrum. And so we've got M over Z, 112, 114, 117 and 120. So these are the different mass to charge ratios. So with Z equal to 1 for the different isotopes in the table here. And we've got a percentage abundance for each. We know that the spectrum is showing 4 peaks, so there are 4 isotopes. So the total of the abundances percentage-wise needs to add up to 100. So that's worth saying that 100 is equal to 22.41 plus 11.78 plus 34.97 plus X. And so X is therefore equal to 30.84%. Might be useful because it says to be determined. Give the symbol, including mass number, of the ion that reaches the detector first. Okay, so the one that reaches the detector first is going to be the ion with the smallest mass. So remember, we're accelerating them to constant kinetic energy, and kinetic energy is equal to 1/2 mv squared. And so if we've got a constant kinetic energy, then the smaller the mass, then the higher the velocity must have to be to reach constant kinetic energy. And so therefore the ion that reaches the detector first is the lightest. So the lightest ion is the 112. The symbol is tin, and we know it's a 1 plus ion. It tells us that in the question. And that's the ion that's going to reach the detector first. The next part of the question asks us to calculate the relative atomic mass. That's using the isotopes and the percentage abundances. So what we need to do is we need to multiply the mass of each isotope by its percentage abundance, like a weighted mean mass. Okay, and then we'll add 114 times by 11.78, and then we'll add 34.97 times 117, and then we'll add the one to be determined, so that's this value here that we determined earlier on. And then we're going to divide all of that by the overall abundance of 100. These are percentage abundances, so we divide through by 100. And so then we're going to carefully input this into our calculators. This is where you might inadvertently make an unforced error if you try and type this all in one go without maybe splitting it up or using brackets correctly on your calculator. And so although it does feel as if it's slightly more time consuming, you could work out each product. So 112 times 22.41, you can work out each product separately. Or if you feel confident to type it into your calculator, type it in twice and see if you get the same answer twice. If you get two different ones, then type it in a third time. So just so that you know you're not making an error by switching a number around or putting a faulty bracket in. So if you do that correctly for this example, you get 116.5. It states in the question to give your answer to one decimal place. When you get to an answer like this, always look back up to see if you can spot something in the question which tells you the number of significant figures or decimal places they would like you to give the answer to. So before you finalise your answer, scan back through the question to just spot whether or not it asks you to give it to a particular level of resolution in your answer. Okay, let's have a look at the next question. So that's question 1. Question 2. This question is also about time-of-flight mass spectrometry, and this time we have to define the term relative atomic mass. Okay, and so I want you to learn this carefully. The weighted mean mass of all the isotopes of an element, and that is compared to 1/12 the mass of an atom of carbon-12. Okay. when that's being marked, the first mark is going to be from the weighted mean mass of all the isotopes of an element, and the second mark is compared to 1/12 the mass of an atom of carbon-12. Next part, a sample of krypton is ionised using electron impact. So we know we've only lost an electron when that happens, and therefore the mass of the ion is equal to the mass of the atom. So we've only lost an electron, so the ion mass and the atom mass are the same to within 4 decimal places. And Z is equal to 1 unless we've got an obvious 2+ ion that's been formed. So the mass spectrum of this sample of krypton has 4 peaks. I've been given all of those. The table shows data from the spectrum. Calculate the relative atomic mass of this sample. So we've been given the relative intensities of the peaks. We do not need to convert them into percentages. We can just use the relative intensity. And so the atomic mass here is equal to the product of the mass to charge ratio times by the intensity for each of the ions. And then on the bottom we've got the sum of all the intensities. And again, just take real care when you're calculating those. So I would work out the top line first, which comes to 3615, and then the sum of the things on the bottom, 43. We're also been told to give our answer to 1 decimal place. Always do that bit of a scan back up higher in the question. And that's our answer. Okay. And I know that you can probably just look at that table and then, you know, that's easy to kind of, without writing down, but don't. For these questions, always show your working. And in fact, in the mark scheme for this, it gives mark 1 for the working and mark 2 for the answer to 1 decimal place. So it's really important for something like this that you do show that working. If you do make an error in typing it into your calculator, getting your brackets wrong, or typing a number back to front, you will still get at least M1. So always, even if it's really straightforward and simple to type it straight into your calculator, always show your working and you will get credit for that. And second steps, for example, if you've made an error that's obvious to the examiner, like you've swapped a number around, you'll get the error carried forward marks. So it's really important that you always give your working out, even if it looks deceptively straightforward. Let's make sure I've put my answer on the answer line to the right number of decimal places. In a time of flight mass spectrometer, ions are accelerated to the same kinetic energy. Kinetic energy of an ion is given by Ke equals 1/2 mv squared, and then it kindly gives us the breakdown of the what the different variables are in the equation. In a time of flight mass spectrometer, each 84 krypton plus ion is accelerated to a kinetic energy of 4.83 times 10 to the minus 16 joules, and the time of flight is 1.72 times 10 to the minus 5 seconds. Calculate the length in meters of the time of flight tube. Okay, so the distance of the time of flight tube, we'll call it D, is equal to velocity times time. That's quite a useful thing to write down first. So we've got Ke equals half mv squared. And so what we're going to want to do is we've been given Ke, that's here. We've been given the time of flight, so we've been given T. And we've effectively been given the mass because we know it's an 84 krypton plus ion. So we've been given, so we've got M there, we've got T here, we've got Ke here. So we're going to use these to calculate the velocity and then use the velocity to calculate the distance. So let's start by calculating the mass of the ion, which is each ion has a mass of 84. And so then we're going to divide that through by Avogadro's number, 6.022 times 10 to the 23. We're also going to divide it by 1,000 because the first calculation would give us the mass in grams and we need the mass in kilograms. So 84 divided by 6.02 times 10 to the 23 and divided by 1,000 gives us 1.395 times 10 to the minus 25. Now, if you get an answer when you're working out the mass that doesn't come to like 10 to the minus 25, if it comes to like 10 to the minus 23, then chances are you've forgotten to convert that mass into kilograms, which you do need. It just reminds you here in the question. So make sure you look really carefully if you can't remember that. So that's our mass. So we can rearrange for velocity squared next. So if we look at this equation for kinetic energy, we can rearrange that so we can say 2ke over m is equal to velocity squared. And so the square root of 2ke over m is equal to the velocity. So we can now put those values in. So the square root of 2 times 4.83 times 10 to the minus 16 divided by 1.395 times 10 to the minus 25. Square root that. So again, take real great care when typing that into your calculator to make sure that you don't make an error when you're typing that in that could subsequently cost you a mark. And also write out your working. So you'll see I've written out even my rearrangement of the equation. I try and do as little in my head that I don't write down. I could do more in my head and not write it down, as I'm sure you can, but I would always try and write out everything that's going on in my head. So calculate this a couple of times if you're not 100% sure, even if you think you've typed it incorrectly. And you should get 83,214.97 as the value for velocity. Okay, and so now we can use the time given in the question. Distance is equal to velocity, 83,214.97 multiplied by the time, 1.72 times 10 to the minus 5. And so our distance comes to 1.43 metres. Let's put that on our final answer line. Question 3. So this is an 8 marker. So quite a substantial question. A pure solid is thought to be calcium hydroxide. So calcium hydroxide is CaOH2. Calcium obviously in group 2, Ca2 plus 2 OH minus ions. The solid can be identified from its relative formula mass. The relative formula mass can be determined experimentally by reacting a measured mass of the pure solid with an excess of hydrochloric acid. The equation for this reaction is shown. The unreacted acid can then be determined by titration with a standard sodium hydroxide solution. You're provided with 50 centimetres cubed of 0.2 moles per decimetre cubed hydrochloric acid. Outline giving brief details how you would conduct an experiment to calculate accurately the relative formula mass of the solid using this method. Okay, so it's thought to be calcium hydroxide. The first thing that we need to do is to do this method. There's a really key part here, is that the unreacted acid can be determined by titration. So we need, for the moles of acid, we can calculate the moles of acid here. This must be in excess, otherwise the experiment won't work. So the number of moles of hydrochloric acid is equal to 50 times 10 to the minus 3 decimeters cubed times by 0.2 moles per decimeter cubed concentration. So we've got concentration times volume. So we've got 50 times 10 to the minus 3 times by 0.2, and that equals 1.0 times 10 to the minus 2 moles. So we must weigh out a smaller amount, taking into account the 1 to 2 mole ratio that we've got here. So we need to weigh no more than 0.5 times 10 to the minus 2 moles of solid. Okay, and then we need to work out the mass of calcium hydroxide. So the MR of calcium hydroxide is 40 plus 16 times 2 plus 2. So that comes to the periodic table 74.1. So the mass is equal to MR times by the number of moles and that gives us 0.3705 grams. So weigh out, so it's got to be less than that. So I say that we want to weigh out, let us say 0.2 grams of solid and it's presumed that. That's the first thing we need to do. And then we're going to react that with our acid. So weigh out 0.2 grams of solid, and number 2, we're going to transfer into a 250 centimetre cubed beaker. And re-weigh the weighing boat to calculate the exact mass of solid. So first of all, we're going to weigh out approximately, accurately, 0.2 grams of solid, which is presumed to be calcium hydroxide, and record the mass to 3 decimal places. We'll transfer the solid into a 250 centimetre cube beaker and reweigh the weighing boat to calculate the exact mass of solid used. Then the next step we're going to do is to measure accurately using a pipette. So we could use a 50 centimetre cubed pipette or two 25 centimetre cubed pipettes. So we're more likely to encounter these in school. So measure accurately using a 25 centimetre cubed pipette, 50 centimetres cubed of 0.2 mole per decimetre cubed HCl. Use 2 pipettefuls. And then add this to the beaker containing the solid. And stir until the solid has completely dissolved. Okay, and so then what I would do then is I would make that up. And we've got 50. By this point, we've got 50 centimeters cubed. I would make up to the solution up to 100 centimeters cubed in the volumetric flask. And then I would titrate 25 centimetre cubed portions of this solution, measured using a 25 centimetre cubed pipette against 0.1 mole per decimetre cubed sodium hydroxide. Until concordant titers are obtained. And because we're at this point, we're titrating the strong acid with a strong base. So we would use practically any indicator with strong acid, strong base, but I'm going to use phenolphthalein indicator. And then calculate the moles of HCl in 25 centimetres cubed of solution and multiply by 4 to calculate a HCl in the original. So then the moles of calcium hydroxide is going to be equal to the original moles of the acid. So the original moles of acid that we calculated was 1 times 10 to the minus 2 minus the number of moles in our solution, the number of moles that have been used up, so the number of moles left over after we've used it up by the calcium hydroxide. So this is giving us the number of moles of hydrochloric acid, which is twice as many moles as the number of moles of calcium hydroxide. So we then need to divide that by 2. And so that will tell us the number of moles of calcium hydroxide that were in our original solid. Okay, and we know how much mass we had. So what we know is that we know that number of moles is equal to mass over mR. So therefore, if we take the number of mass divided by the number of moles we've calculated, so the mass being the mass that we weighed out, which is close to 0.2, divided by the number of moles we've calculated doing this calculation, is going to equal the MR that we're trying to calculate. So the MR is going to be the mass weighed out, which is so we're going to be weighing out 0.2 grams of solid, and we've recorded that to 3 decimal places. So it's this amount recorded accurately after we've calculated the mass of the weighing butt so that we can do it exactly. So that's the mass that's going in here. And the number of moles of calcium hydroxide, this, is equal to the original moles of the acid that we started with. Take away the amount that we've calculated in our titrations, which we've multiplied by 4 to account for the fact we made it up to 100 centimetres cubed. So we did it in portions of 25 centimetres cubed to enable us to get concordant titers. If we had just done 2 titrations on the 50, we may not have got concordant titers and we would have used it all up. So we needed to make it up to at least 100. We could have made it up to 250. But I think 100 is sensible because that gives us 4 attempts to get concordant titers. We've titrated that against sodium hydroxide that we know of a known concentration. So the amount of sodium hydroxide in moles that we've used is equal to the amount of moles of hydrochloric acid that's there. And then we take the difference between the original moles of hydrochloric acid and the amount that was present in the solution, divide that by 2 to give us the number of moles of calcium hydroxide, and then do the final calculation. That's an 8 marker. A fair old amount needed there to get that calculated. Part B, a 3.56 gram sample of calcium chloride was dissolved in water and reacted with an excess of sulfuric acid to form a precipitate of calcium sulfate. The percentage yield of calcium sulfate was 83.4%. Calculate the mass of calcium sulfate formed. Okay, so calcium chloride, CaCl2, aqueous, is reacting with sulfuric acid, an excess of that, and that's going to form calcium sulfate, which is a precipitate, plus water. Oh, hang on a minute, and is it going to produce? So sulfuric acid going to form 2 HCl aqueous. There we go, and so we've got 1:1 mole ratio of calcium chloride to calcium sulfate. So the number of moles of calcium chloride is equal to 3.56 divided by the MR of calcium chloride, which is 111.1. So that gives us a number of moles of calcium chloride as 3.204 times 10 to the minus 2. And then that's going to be equal to the moles of calcium sulfate that would be formed if the percentage yield was 100%. So that would be the theoretical mass of calcium sulfate would equal to 3.204 times 10 to the minus 2 times by the MR of calcium sulfate, which is 83.4. Times by 156.2. So the mass of calcium sulfate is 3.204 times 10 to the minus 2, that's the number of moles of calcium sulfate that we could form, times by the percentage yield, which is the amount that we're making less than 100%, times by the MR of calcium sulfate. So we do all of that, and we get 3.3, and let's have a look and see a suitable number of significant figures. 639, so actually suitable number of significant figures looking at the question is 3 significant figures, so it's 3.64 to 3 significant figures. Question 4. The concentration of dilute hydrochloric acid can be found by titration using a standard solution of barium hydroxide. Calculate the mass in grams of solid barium hydroxide needed to prepare 250 centimetres cubed of 0.1 mole per decimetre cubed barium hydroxide solution. So if we wanted to calculate, we want a 0.1 mole per decimetre cubed solution of barium hydroxide. That's 0.1 moles in a litre. And so we would need 0.1 times by 171.3 if we wanted to calculate a litre's worth. But we don't actually want to make a litre. We want to make 250, so that's 1,000 divided by 250, which equals 4 times less. We want to make a quarter of it, so we need to divide that through by 4, and so our answer to that is 4.28 grams needs to be worked out. Part B, the mass of barium hydroxide from part A. Okay, so mass 4.28 grams. I'm just going to write that there so I can't forget. Is dissolved in a beaker containing 150 centimetres cubed of distilled water. Describe how this solution is used to make 250 centimetres cubed of the barium hydroxide solution. So this is about how to accurately make a volumetric solution. So number 1, we're going to use a funnel to carefully transfer the solution into a 250 centimetre cube volumetric flask. It'll be really important to get that term right, volumetric flask. Then number 2, use a wash bottle of distilled water to wash the beaker and funnel into the volumetric flask. And then part 3 is going to be remove the funnel and fill to just below the line, stopper and invert to mix, and then use a dropping pipette to add final drops until those drops of distilled water until the meniscus is on the line. And then finally invert to mix again. And then we have our standard solution. Before the first titration, the 25 centimetre cubed pipette is rinsed with a small volume of the 0.1 mole per decimetre cubed barium hydroxide solution. State why it is good practice to rinse the pipette in this way. And that's to ensure the concentration is not affected by any water in the pipette. So if we previously washed the pipette with water, there might be droplets of water in there that would affect the concentration, and we want it to be exactly 0.1 mole per decimetre cubed barium hydroxide, or at least at the concentration that we have calculated. So the concentration is known accurately. Hydrochloric acid is added to the burette using a funnel. State why it is good practice to remove the funnel from the burette before the titration to ensure no drops of HCl fall into the burette during the titration. That would affect the volume reading from burette. Okay, and that would spoil the reading from the burette. In a different experiment, 0.952 grams of solid barium hydroxide is used to make 250 centimetres cubed of standard barium hydroxide solution. 25 centimetres cubed of this barium hydroxide solution reacts exactly with exactly 24.50 centimetres cubed of hydrochloric acid, calculate the concentration of hydrochloric acid. So barium hydroxide is in group 2, so it's BaOH2, and it is reacting with hydrochloric acid, so it's going to need to be balanced like so, to ensure that we've got all of it fully neutralised. I think Alexa wanted a word in sideways there. Calculate the concentration. I've lost my train of thought. Okay, so we've got it's a 2 that way around. It's a 2-to-1 ratio. So we've got we'll work out how many moles of barium hydroxide we have, and we will have twice as many moles of hydrochloric acid. So we've got 0.952 grams of solid barium hydroxide divided by the MR of barium hydroxide, which is 171.3. They were kind enough to tell us that in the first part of the question. I'm pretty certain. There we go. We didn't need to calculate that. So the number of moles of barium hydroxide in the solid that we've used is 0.95. Let's see, we'll make my calculator come on. It's gone off. Is 5.558 times 10 to the minus 4 or minus 3. And then that's the amount that is in 0.952 grams. What we've then done is we've made that up to 250, and we've taken 25 centimetres cubed of that portion. Okay, so the number of moles of barium hydroxide in 25 centimetres cubed is 10 times less than that. So we've got to divide that by 10 because we've used 25 out of 250. So 250 over 25 is equal to 10. So we've got to divide it by 10, which is 5.558 times 10 to the minus 4 moles of barium hydroxide. It's a 1-to-2 ratio, so we now need to multiply that by 2. And that's going to give us 0.00111 moles. So that's the number of moles of hydrochloric acid. And we know we've got the concentration is equal to moles divided by volume. So we've got 0.00111 divided by the volume, which is 24.50 times 10 to the minus 3. And so our concentration is equal to 0.045 moles per decimetre cubed. uncertainty in the 25 centimetre cubed solution from the pipette is plus or minus 0.05. The total uncertainty in the 24.5% centimetre cubed solution from the burette is plus or minus 0.15. Calculate the total percentage error. Okay, so we need to look at the amounts that we have measured. So it says that the uncertainty, we've got one reading from the pipette, because we suck it up and we read to one mark. So we've got 0.05 divided by 25 measured. That's the uncertainty from the pipette, which is the plus or minus 0.05 divided by 25. Tells us the total uncertainty for the burette. So we're taking into account both readings. So we need to add 0.15 divided by 24.50. So they're the uncertainties. So we need to then calculate the percentage error by multiplying that by 100. Do this bit first. 0.05 divided by 25 plus 0.15 divided by 24.5. Multiply that by 100. And that gives us 0.81%. Question 5. The diagram shows some reactions of aqueous iron ions. So this is 3.2.6 if you're looking for that as part of the syllabus. Ions in aqueous solution. So we've got iron hexaaqua 3+ reacting with conc HCl in reaction 2, reacting with sodium carbonate in reaction 1. Reaction 3 is reducing it from iron 3+ to iron 2+, and then it's reacting with concentrated ammonia to make a precipitate. So if we have a look at these reactions of iron 3+ ions, then we can actually fill in all of these and then have a go at answering the questions. So solution containing complex iron L. So when we use concentrated HCl, we're doing a ligand substitution reaction. And that's replacing water ligands with chloride ligands. Chloride produces a 4-coordinate complex, which is tetrahedral. And then we need to work out the charge. It's 3+ on the metal ion. Each chloride ligand is 1-, so 3+ minus 4 is -1 overall. That's a ligand substitution reaction. Reaction 1 is a precipitate. So the iron hexaaqua 3+ ions are going to act as their acidic ions. So they're going to do a neutralization reaction. And they're actually going to form the hydroxide ion complex. So we're going to have the Fe H2O6 3+, and it's going to react. 3 of the water molecules are going to give up a hydrogen ion to react with 3 carbonate ions. So this is the hexaaqua 3+ ion acting as an acid, and it's going to make therefore 3 carbon dioxides, 3 water molecules, and it's going to make the solid, which is the hydroxide. and we'll still have 3 waters. And that is a solid complex. How many of those? Let's just do some balancing now. So that's precipitate J. Reaction 3 is a reduction. Fe3 plus E minus goes to Fe2 plus. And then finally we've got the reaction with concentrated ammonia. So we're going to form precipitate M. So this is also going to form hydroxide precipitate. Okay. Right, so let's have a look at the questions. Give an equation for reaction 1. So the formula of J is going to be the FeOH3 H2O3 solid precipitate, and that colour is going to be a brown precipitate or a rust brown. Gelatinous precipitate. And the equation for that, which we've actually already written out, Fe, so 2 lots of Fe H2O 6 3 plus plus 3 carbonate ions forms 3 carbon dioxides plus 3 waters plus 2 lots of our precipitate complex. Next question is to give the formula of L and an equation for reaction 2. So L is our tetrachloro iron 3 plus. So the formula is FeCl4 minus, and the equation is the FeH2O 6 3 plus 4 Cl minus FeCl4 minus plus 6 H2O. That's our ligand substitution reaction. Suggest a reagent for reaction 3. So a sensible reagent for reaction 3 would be acidified zinc. So zinc in sulfuric acid. That's our reducing agent of choice when it comes to transition metals. You may remember doing this one. You might have done the experiment where you would use zinc acidified with a solution of vanadium. So something like ammonium metavanadate, vanadium in its +5 oxidation state, and you would see it being reduced through different colours down to purple vanadium 2+, from yellow vanadium in its +5 oxidation state in the vanadate ion. So zinc is a very good reagent of choice for the reduction of transition metals. D, give the formula of precipitate M and state its colour. So I'm just going to back up and see what M is. Okay, so M is the hydroxide precipitate of the 2+ ion. So it's and the colour is it's a moss green. Gelatinous precipitate. Very watery precipitates because there's lots of water molecules still coordinated to the metal ion. Okay, this question is a 6-mark question, so it'll be a 3-stage question. It says transition metal complexes have different shapes and many show isomerism. Describe the different shapes of complexes and show how they lead to different types of isomerism. And you should use examples of complexes of cobalt-2 and platinum-2. So this is going to be a 3-stage question. So let's try and pick out what the 3 stages might be. I'm just circling here, describe the different shapes of complexes. I would think it's likely that is stage 1. And again, you'll have to use that in terms of cobalt-2 and platinum-2. And show how they lead to different types of isomerism. Now, there's 2 types of isomerism. So stage 2, cis-trans, seems likely. And again, using examples of cobalt and or platinum. And then 3 is optical isomerism. And I should say again, using examples of either cobalt or platinum. So it's always got to come back to using examples from these 2 transition metal ions to give us our examples. Remember, to get into level 3, you're going to have to cover all 3 stages, virtually complete. So let's have the first one then. So different shapes of complexes. And using cobalt-2 and platinum-2. So we could have tetrahedral, and we could have cobalt it's a cobalt-2 plus complex, but with 4 Cl- ions. That's going to be 2- overall, and that is tetrahedral. We could also have the cobalt hexaaqua, +2, which is octahedral. And then we could have square planar. And we could have the cisplatin. Which is a neutral complex, so that is square planar. Now, we have got other shapes, so we could have linear complexes, but there aren't any linear complexes that you've learned about that have got platinum or cobalt in the middle. So we're not going to include those. An example might be this silver ammonia complex, which is linear. But we're not going to include that because we've not been told to look at different types of central transition metal ions other than cobalt and platinum. So we've got the shapes, and now the next part then is going to be cis-trans isomerism. And here we could have cis and trans plotting. So let's draw the trans plotting again. And we could also draw, so that's the cis plotting. And this one is trans plotting. So it's like 180 degrees there between the two chlorine ions, and here the chloride ions have got 90 degrees. The other type of cis and trans that we could have would be in an octahedral complex, such as this one here. With ethane 1,2-diamine, and that would be trans, and the cis version of that .90 degrees between the two ammonia ligands here, and 180 degrees between the two ammonia ligands here. And then finally, optical isomerism. And for this one, we can actually just show the cis, we can show the opposite optical isomer for this cis version. These optical isomers with the ethane 1,2-diamine ligands. So if you just go back through this question then, this is a question I probably would have ended up going on to an extra page of continuation, because I've drawn my diagrams out to show these examples, and I think it's an easy question to run out of space on. So if I compare this now with the mark scheme, so stage 1 was looking, as we suspected, it was looking at shapes of complexes, so that's good, that's stage 1. First of all, for 1A, it wanted an octahedral or a 6-coordinate diagram. So let's have a look, that's this one here, so that's stage 1A. And tetrahedral for 1B, or square planar or 4-coordinate diagram. So we've got 1B, we've got a tetrahedral one, and we've got a square planar one. So we've got stage 1 is complete. Stage 2 wanted cis or trans isomerism. So 2A wanted cis-trans isomerism in either square planar and or octahedral. So we've got cis and trans in square planar, so that's 2A in square planar, and we've got it in octahedral. And 2B diagrams showing cis and trans isomerism in a square planar complex. So that's 2B. And 2C was diagrams showing cis and trans isomers in both isomers of octahedral complexes, e.g. draw cis and trans. So we've got got that one here, so that's 2B. So we've got 2A and 2B. And then finally, stage 3, optical isomerism, we've got in octahedral complexes, so that's 3A, we've drawn octahedral, occurs with specific bidentate ligands, so we've got the one with ethane 1,2 diamine, so that gives us 3B, and draw both optical isomers, which is 3C. So we've done that. So we've got all of them, and that's going to be giving us all 6 marks. The only other thing to note is that the mark scheme required answers to be illustrated using diagrams of at least 2 specific examples of pairs of cobalt or platinum complex isomers. So how many of those did we use? We needed to use at least 2, but if we're looking at the pairs, we've got 1 pair, we've got 2 pairs, and we've got 3 pairs here. So we're going to get the marks there for getting into stage 3. Question 6. This question is about cobalt chemistry. Give the electron configuration of the cobalt atom and of the cobalt 2+ ion. State 3 characteristic features of the chemistry of cobalt and its compounds. So we could write this. We look on the periodic table and you count along the D block. You'll see that cobalt is the 7th metal along, so we could simply write argon 3D7 for S2, or we could write it out in full, 1S2, 2S2, 2P6, 3S2, 3P6, 3D7 for S2, and that's for cobalt. Cobalt 2+, we've got to remember that 4S both fills and empties before 3D, so it's argon 3D7, or again written out in full, 1S2, 2S2, 2P6, 3S2, 3P6, 3D7, and then 3 characteristic features. Now, chemistry of cobalt is determined by the fact it is a transition metal. It has a stable ion with a partially filled D subshell. So any of the classic characteristic properties of transition metals will do. So we could say that cobalt shows variable oxidation states. Cobalt and its ions can act as catalysts. Cobalt ions form coloured complexes. And compounds. Ethane 1,2 diamine can act as a bidentate ligand. When cobalt hexaqua 2+ ions are treated with an excess of ethane 1,2 diamine, the water ligands are replaced. And then we've got 3 sections for this 7-mark question. What is meant by the term bidentate ligand? First bit. Explain with the aid of an equation the thermodynamic reasons why this reaction occurs. And draw a diagram of the complex ion. So we've got to make sure we do all 3 of these things. Number 1. This is a molecule containing 2 lone pairs of electrons, each of which forms a coordinate bond to the central metal ion. might be worth putting a separate coordinate bond to the central metal ion. Number 2, explain with the aid of an equation the thermodynamic reasons why this reaction occurs. So this is to do with entropy. So what we're going to do is liberate water molecules and replace them with bidentate ligands. So overall entropy is going to increase. So we've got CO, H2O, 6, 2 plus. Each of these is going to be a bidentate ligand, so 2 lone pairs. So we're going to need 3 of them to fill the coordination sphere of that cobalt. So 3 lots of ethane 1,2-diamine. And that's going to form our octahedral complex with 3 bidentate ligands plus liberating 6 water molecules. And then on the left hand side we've got 4 particles, and on the right hand side we've got 7 particles. So we have an increase in entropy. So delta S is positive and delta G equals delta H minus T delta S, and so delta G negative. So the reaction is spontaneous. And finally we need the diagram of the ion that's formed. It's a bit squashed up there. I'm going to try and make that look a bit better. That's better. Oh, and that's reminded me of my previous diagrams. Did I put enough? Oh, I didn't put enough hydrogens. There we go. On my octahedral complexes. There we go. That's better. Okay, so we've drawn our diagram to show the structure of the complex ion formed. So because this is quite a long question, so going to just go through the mark scheme, double check we've got all the points here. Let's move this to the red pen. There we go. So the first part is 2 atoms that each donate a lone pair of electrons. So a molecule containing 2 lone pairs of electrons, each of which forms a separate coordinate bond to central metal ion. So we've got the marks there. Then we've got cobalt hexaaqua 2 plus 3 lots of ethane 1,2-diamine. Okay, so that equation is correct. Increase from 4 particles to 7 particles. Increase in entropy, delta S is positive. Delta G is negative, also needs to be mentioned. And then we've got the diagram here with the right number of hydrogens. That's good. Excellent. We've got all the marks there. Okay, looking at question 7, we've got an equilibrium question about the decomposition of nitrogen dioxide into NO and O2. It's an endothermic reaction. Let's have a look at the first part. We're going to be looking at a gas calculation to calculate Kp in the end, I think. So 0.317 sample of nitrogen dioxide is placed in a sealed flask and heated until equilibrium is reached. At equilibrium, the flask contains 0.120 moles of oxygen. Calculate the mole fractions of each substance at equilibrium. So we'll start by creating ourselves a table, and our table is going to have the 2NO2 in equilibrium with 2NO and O2. I'll use that as the top of the table. And we've got initial moles, we've got the change, and we've got the equilibrium. So just let's add some lines just to help us a little bit with this. Add a little table. Okay, so initially we've got 0.317 sample of nitrogen dioxide, and we've no NO and no O2. And at equilibrium we've got 0.120 moles of oxygen. So that's gone up by 0.120. Now the mole ratio of oxygen to NO is 1 to 2, so that means this must have gone up by 0.240. And so that means that the NO2 must have gone down by 0.240. So at equilibrium we've got 0.077 of that. So those are our equilibrium moles. Mole fraction then is the number of moles divided by the total number of moles. So let's total moles is the sum of each of these. So 0.077 plus 0.240 plus 0.120. So the answer to that is 0.437. So the mole fraction is the equilibrium moles divided by the total number of moles. So for the first one it's 0.077 divided by 0.437, which is 0.176. And then for the next one it's 0.240 divided by 0.437, which is 0.549. And then for the oxygen it is 0.120 divided by 0.437, which is 0.275. So let's make sure we get those in the right order. 0.549 and 0.275. These little tables are really, really useful for doing calculations like this. The total pressure in the flask is 120 kilopascals. Calculate the partial pressure of NO2. So the partial pressure is equal to the mole fraction multiplied by the total pressure. So that for NO2 is 0.176 multiplied by the total pressure, which is 120. And that comes to 21.12 kilopascals. So in this part, we're looking at the same equilibrium, but with 3 new mole fractions, and they've given us a value for Kp. First part of the question we have to answer is to give an expression for Kp. So we obviously first look to the product side of the equilibrium to write the product of the partial pressure of NO times by the partial pressure of O2, that's partial pressure of NO squared, because the mole ratio is 2 to 1. And then we have the reactant side of the expression, and this is the partial pressure of NO2, and that is squared, because the mole ratio is 2. Use your expression and the data in the table to calculate the total pressure in kilopascals in the flask. So remember that partial pressure is equal to mole fraction multiplied by total pressure, which I'm going to use a big P for. So we can rewrite this expression as the mole fraction of NO squared times by big P squared multiplied by the mole fraction of oxygen, which is 0.230, times by big P, divided by the mole fraction of NO2 squared times by big P squared. So obviously they cancel. So Kp is 59.7 times 10 to the 3 pascals. And so we can now start to calculate this expression. So I'm going to do the numbers first. So I've got 0.460 squared times by 0.230, and then I'm going to divide through by 0.310 squared, and so I get a value of 0.506 for P is equal to 59.7 times 10 to the 3. So P is equal to 59.7 times 10 to the 3 over 0.5064. And that gives me 117.89 kilopascals. So a sensible number of significant figures, everything given to 3, so 117.9 kilopascals. In part D, we're asked to consider the equilibrium mixture being compressed into a smaller volume. So compressing the mixture into a smaller volume will increase the pressure. Have a look at the equilibrium. Increasing the pressure will send the equilibrium to the side with fewer moles, which is to the left. that will reduce the amount of oxygen. So the yield on the oxygen will decrease. However, this does not affect the Kp. The value of the equilibrium constant remains the same. There'll be no change to the Kp. The equilibrium mixture in part C is allowed to reach equilibrium at a lower temperature. Explain why the equilibrium yield decreases. So looking right back to the start, when we observed that the enthalpy change for this is endothermic. In fact, I think I might have even written that down right at the top here. Okay, it's endothermic for this reaction. So endothermic reactions, just check what we're doing to it. We're cooling it. Okay, so endothermic reactions, if we cool them down, they will do the exothermic direction. So that will move the equilibrium to the left to oppose the decrease in temperature. So the reaction is endothermic, cooling the reaction will cause the equilibrium to shift in the exothermic direction, which is towards the reactants, which is the left-hand side, and that will reduce the yield of oxygen. Question 8. This question is about group 7 and their compounds. Part A. Chlorine is added to some drinking water supplies to decrease the risk of people suffering from diseases such as cholera. State why the amount of chlorine added must be controlled. And this is because chlorine is toxic. And that's why we would want to add it to reduce the risk of disease, because cholera is going to be killed by, is a bacteria, is going to be killed by chlorine. But we don't want that amount of chlorine to cause harm to people drinking the water. Part B. Give an equation for the reaction of chlorine with water to form a solution containing 2 acids. Okay, so this is one of those equations that you have to learn from your group 7 material in year 1 A level. So chlorine plus water makes a mixture of HCl and HClO. This is a disproportionation reaction, so you can describe that in the next part. Explain with reference to electrons why this is a redox reaction. So we're explaining this with reference to electrons, and so need to be very careful to make sure we are exactly answering that question. So if we think about it, chlorine in Cl2 is going to both chlorine 0 to -1 in HCl. And if we work out the oxidation state of chlorine in HClO, oxygen is -2, hydrogen is +1, and so this must be +1. So chlorine has gained electrons to form Cl minus, and chlorine has lost electrons to form ClO minus. Okay, so the really important thing is that you've got to explain this with reference to electrons. So redox with reference to electrons is talking about oil rig. Oxidation is loss, reduction is gain. So we need to be talking about the gaining of electrons. So that's reduction. And the loss of electrons, that's the oxidation. A student bubbles chlorine gas through a solution of sodium iodide. State the observation the student would make. Give an ionic equation for the reaction. So chlorine is more reactive than iodine, and therefore it will displace iodine from a solution of iodide. So the equation that we want is going to be chlorine plus 2I minus goes to 2Cl minus plus I2. And so this helps us with the observation that we would see purple vapour of iodine, or a purple solid being formed. Let's have a look. Are we in solution? Bubble of chlorine gas through a solution of sodium iodide. Okay, so we're not going to see a purple solution. We're going to basically see a brown solution. We're going to see iodine in solution here. And that's a brown solution. So we're in solution, so we're not going to see some purple vapour of iodine. So in this question we have the student adds a few drops of concentrated sulfuric acid to a small amount of solid sodium iodide. So the iodide is a strong reducing agent, and it can reduce the sulfur in sulfuric acid. 2 gaseous sulfur-containing products are formed. Give an equation for the formation of each of these sulfur-containing products, and state the role of sulfuric acid in the formation of these products. Okay, so sulfuric acid is acting as an oxidizing agent. In these reactions, and the iodide is acting as a reducing agent. So the half equation for the iodide is 2I minus goes to iodine plus 2E minuses. Okay, and that's going to help us in creating these equations. The two products, the gaseous containing sulfur products, the gaseous sulfur containing products are SO2 and H2S. And so in equation 1 we're going to go from SO4 2 minus, where the sulfur is in its +6 oxidation state, to SO2, where the sulfur is in its +4 oxidation state. So one lot of the iodide is all we're going to need here to do that, because we're just going to need 2 electrons to take it from +6 to +4. So we're going to have 2 I minuses on this side and an iodine on that side. And then we need to look at the number of oxygens. So we're going to turn any spare oxygens in the SO42 minus into waters on the other side. So we've got SO42 minus on this side, and we've got SO2 plus, we're going to need 2 waters to soak up those extra oxygens. And then if we're making waters on the right hand side, we're going to need some H pluses on the left hand side. How many of them? Well, 2 waters is going to need 4 H pluses. So that's how to construct the first equation. And the second equation, we're going from SO42 minus, which is in its +6 oxidation state, to H2S, where the sulphur is in its -2 oxidation state. So we're going from +6 to -2. And so that means we're going to need actually 4 lots. That overall change is 8 electrons. So we're going to need 4 lots of the iodine, the iodide to iodine, to balance that off. So 4 lots, we're going to therefore need to have 8 I minuses and 4 I2s. Looking at the number of sulphurs, oxygens with the sulphate, we've got SO42 minus, so we've got to make 4 waters, and then we're going to need to add our H pluses. So we need 8 H pluses to make the waters and another 2 to make the H2S. So in total we're going to need 10 H pluses, and that's how we construct that equation. So these are 2 equations that you can either remember, or you can, as I've just done there, construct them from first principles by considering the oxidation states of the sulphur in each example, and then balancing the equations using the right multiple of the reducing agent, the redox equation for the reduction, and balancing with waters and hydrogen ions, and you can get to the answer by doing that. Look at part E. The student adds a few drops of acidified silver nitrate solution to a solution of an unknown impure sodium halide. The student observes bubbles of gas and a colourless solution. The student bubbles the gas through calcium hydroxide and a white precipitate forms. Deduce the identity of the sodium halide and suggest the identity of the gas. And give an ionic equation for the formation of this gas from the impurity. Okay, so the student has added silver nitrate to an unknown halide, and we get a bubbles of gas and a colourless solution. So we haven't got a white, a cream, or a yellow precipitate, which we would have if we had chloride, bromide, or iodide ions present. So this is a little bit of a trick question, I think, because the identity of the halide must therefore be sodium fluoride, because we haven't made a chloride, bromide, or iodide precipitate. The identity of the gas comes from the impurity, because it turns lime water, which is calcium hydroxide solutions, that is lime water, and a white precipitate is going cloudy. So this is a gas that turns lime water cloudy, so it must be carbon dioxide. And so the identity of the ionic equation for the formation of the gas from the impurity, so the ionic equation is from a carbonate, so it must be CO3 2 minus plus 2H plus goes to CO2 plus H2O. Part F, the ClF2 plus ion contains 2 different group 7 elements. chlorine and fluorine. Use your understanding of the electron pair repulsion theory to draw the shape of this ion. Include any lone pairs that influence the shape. Explain why the ion has the shape you've drawn, and suggest a value for the bond angle. Okay, so let's have a look then. Cl is the central atom and it has 7 electrons. Fluorine brings 2, 1 for each bond, and the positive charge means we need to remove an electron overall. So the total number of electrons is 7 plus 2 minus 1, which is 8. So the shape is based on a tetrahedron. With 4 pairs. It's making 2 bonds, so 2 bonding pairs and 2 lone pairs. So the explanation is the molecule has 2 lone pairs and 2 bonding pairs. Electron pairs repel. To be as far apart as possible. And lone pairs repel more than bonding pairs. So the bond angle, if it was a tetrahedron, would be 109.5 degrees, but it has 2 lone pairs, so it's going to be similar to the bond angle of water. So we'd say 109.5, and we'd take off 2.5 for each of the lone pairs roughly, so we would say maybe something like 104.5 degrees. Similar to water, very similar molecule to a water molecule. Magnesium is used in the extraction of titanium from titanium 4 chloride. Give an equation for this reaction. So titanium 4 chloride and magnesium, so Mg plus TiCl4 is going to go to titanium plus magnesium chloride. So we now need to make sure that we have balanced this. So magnesium is in group 2, so it can bond to 2 chlorines. So we're going to need 2 lots of magnesium in order to use up the 4 chlorines that are provided by the titanium tetrachloride. So that is a displacement reaction. Okay, question 9. Chlorine is used to decrease the number of microorganisms in water. When chlorine is added to water, there is a redox reaction as shown by the equation. We've just been looking at that one in the previous question, so it should look quite familiar. Deduce the oxidation state of chlorine in HClO and the oxidation state of chlorine in HCl. So as we're looking at this, we know that hydrogen has to be in its +1 oxidation state and oxygen in its -2, which means that to balance, the chlorine must be in a +1 oxidation state in HClO, and in the HCl, hydrogen must be +1, so the chlorine must be -1. Give 2 half equations to show the oxidation and reduction processes that occur in this redox reaction. Okay, so both times it's going to be chlorine that is both oxidised and reduced. So to piece this together, we're going to show chlorine, and this time it's going to go to HClO. So we're going to need to make 2 of those to make that balance. Anywhere where we've got an oxygen on the right hand side, we're going to need a water on the left hand side. So Cl2 plus H2O is going to go to 2 HClO. So we're going to need 2 waters. I've not quite left myself enough room for that, so plus 2 waters because we've got 2 HClO, so 2 oxygens. And then we're going to need to balance that with some hydrogen ions because we've got 2 hydrogens on the right, but we've got 4 on the left. So we're going to need to balance that with 2 hydrogen ions on the right hand side, and each chlorine has gone from a Cl0 to a Cl +1, which means that we must have lost 2 electrons. For the reduction half equation, we've got Cl2, and this time it's going to 2HCl. And so we just need to use electrons and hydrogen ions to balance this. So the 2 hydrogens on the right hand side become 2H+. And this time the chlorine's gone from 0 to -1, so it must have gained 2 electrons. Chlorine is reacted with cold aqueous sodium hydroxide in the manufacture of bleach. Give an equation for this reaction. So we have chlorine plus NaOH. I'll balance it in just a moment. The products from this, you need to learn this. So make sodium chloride plus NaClO plus H2O, and then we need to balance this equation. So if I take a look at it, we're going to need 2 sodium hydroxides to make that balance. Next part now, we've got a calculation. The concentration of ClO- ions in bleach can be found by reaction with iodide ions. The overall equation for this reaction is shown. A sample of bleach solution was found to contain ClO- ions with a concentration of 0.0109 moles per decimeter cubed. Potassium iodide is added to a 20 centimeter cubed portion of this bleach solution. Calculate the mass in milligrams of potassium iodide needed to react with all the ClO ions in the sample of bleach. Okay. And give 1 observation during this reaction. Okay. So the first thing we need to do is calculate the number of moles of ClO- ions in 20 centimetres cubed of that concentration, 0.0109 moles per decimeter cubed. So concentration of ClO minus ions times the volume is what we need. So the number of moles of ClO minus is equal to concentration times volume is equal to 0.0109 times 20 times 10 to the minus 3, and that equals 2.18 times 10 to the minus 4 moles. And then we need to look at the mole ratio. It's 1 to 2, so we need twice as many moles of potassium iodide. So the number of moles of Ki that we need is equal to this, 2.18 times 10 to the minus 4 times 2. So that is 4.36 times 10 to the minus 4. And the next thing we need to do is calculate what that is in grams, that number of moles in grams. So we do moles times MR. It's going to give us the mass in grams. So the MR is, using the periodic table, is 166. And we're going to multiply that by the number of moles, 4.36 times 10 to the minus 4. And that gives us a mass of 0.072376 grams. And then times by 1,000 will give us 72.4 milligrams, which is what we've been asked to give the units. So that is 72.4 milligrams. And what would we see? Okay, so we're going to be forming iodine in solution. So the solution would turn brown due to dissolved iodine being formed. Question 9 part E. Potassium chlorate 7 at KClO4, so this is chlorine in its +7 oxidation state, is used in fireworks. When potassium chlorate 7 decomposes, it produces potassium chloride, KCl, and oxygen, O2. Give an equation for the decomposition of potassium chlorate 7 and then calculate an enthalpy change for that. So we've got KClO4 is going to go to potassium chloride, KCl, and oxygen, and then we just need to balance it. It's going to be obviously 2O2. And then we've got the enthalpy change of formation. So the enthalpy changes for this reaction, so we've got potassium chlorate 7 with an enthalpy change of formation of -434, and we've got potassium chloride with an enthalpy change of formation of -436, and so in total the enthalpy change is going to be equal to the enthalpy change of formation of products, -436, take away the enthalpy change of formation of the reactants, -434. So the answer is -2 kilojoules per mole. And the end of that question. Question 10. Calcium hydroxide is almost insoluble in water, but it reacts with dilute hydrochloric acid. A student adds 100 centimetre cubed of 0.1 moles per decimetre cubed hydrochloric acid to 0.6 grams of solid calcium hydroxide. Show by calculation that the calcium hydroxide is in excess. So we've got to calculate the number of moles of HCl, which equals concentration times volume, which equals 100 times 10 to the minus 3 times 0.1, which is 10 times 10 to the minus 3 moles. 0.6 grams of solid sodium carbonate divided by the MR, 74.1, is equal to 0.00810. That's the number of moles of calcium hydroxide. So it would require twice as many. Would require n times 2, which is equal to, so it's that value, which is 0.0162 moles of HCl, and we only have 0.01 moles of HCl. So the calcium hydroxide is in excess. Part B then, the final mixture contains a saturated solution of calcium hydroxide, 293 Kelvin. At 293 Kelvin, the solubility of calcium hydroxide in this solution is 0.4 grams per decimetre cubed. Kw is 6.8 times 10 to the minus 15 moles squared per decimetres to the minus 6. Calculate the pH of this solution. So this is the pH of a strong base. So the final mixture contains a saturated solution. So we've got, what we know we've got is 0.4 grams per decimetre cubed. And that we can calculate the number of moles, which is equivalent to 0.4 divided by 74.1. Which is 5.40 times 10 to the minus 3 moles per decimetre cubed. So the concentration of CaOH2 is equal to 5.40 times 10 to the minus 3 moles per decimetre cubed. The concentration of OH minus is 2 times that, because each mole of calcium hydroxide produces 2 moles of hydroxide in solution, completely dissociated, because it's a strong base. 5.40 times 10 to the minus 3. And so that is equal to 0.0108 moles per decimetre cubed. Kw is equal to the concentration of hydroxide times by the concentration of hydrogen ions. This is what we want to know to calculate pH, of course, the hydrogen ion concentration. So we need Kw over OH minus, which equals 6.80 times 10 to the minus 15 divided by 0.0108, and that gives us 6.3. So look, I just timed, I'll do it in my calculator rather than in my head. 6.8 times 10 to the minus 15 divided by 0.0108. And that gives me 6.296 times 10 to the minus 13 is the hydrogen ion concentration. And then we're going to do the negative log to the base 10 of 6.296 times 10 to the minus 13. And that gives us a value of 12.200. And it says give your answer to 2 decimal places, so we need to be careful to do that. That's our answer for the pH of that strong base. Which statement about pH is correct? The pH of a weak base is independent of temperature. Think about that one first of all. The pH of a weak base is independent of temperature. That's not correct, because as you change the temperature, the amount of dissociation will change, and therefore the pH will change. The position of the equilibrium will move, so that's not correct. At temperatures above 298, the pH of pure water is less than 7. That is correct. So let's have a look at the next ones. The pH of 2 mole per decimetre cube nitric acid is approximately 0.3. Well, it's a strong acid, so it's going to be negative log to the base 10 of 2. It's a monoprotic acid. So let's have a look at that, just to prove that that one is incorrect. So the negative log to the base 10 of 2 is minus 0.3, so that's incorrect. The pH of a 0.1 mole per decimetre cubed sulfuric acid is greater than that of 0.1 mole hydrochloric. Now it's going to be less than that because we'll have twice as many dissociated hydrogen ions, so it'll have a lower pH. So that's not right, so it is B. It is the correct answer. The ionic product of water, Kw, equals 2.93 times 10 to the minus 15 moles squared decimeters to the minus 6 at 10 degrees C. What is the correct expression for Kw? So Kw is C. That's this one here. Part B, calculate the pH of pure water at 10 degrees C. So at 10 degrees C, H2O is in equilibrium with H plus and OH minus. The concentration of H plus is equal to the concentration of OH minus in pure water, so we can write Kw is equal to H plus squared. So the calculation for H plus is equal to square root Kw. So So we need to do the square root of 2.93 times 10 to the minus 15, and that gives us a H plus of 5.413 times 10 to the minus 8, and pH is the negative log to the base 10 of the 5.413 times 10 to the minus 8, which is 7.2, and we want our answer to 2 decimal places, so reading from my calculator, that's 7.27. Suggest why this pure water at 10 degrees C is not alkaline, and that's because the concentration of H plus is equal to the concentration of OH minus. Calculate the pH of a 0.0131 mole per decimeter cubed solution of calcium hydroxide at 10 degrees C. So we have calcium hydroxide, concentration is 0.0131. So the hydroxide concentration of this strong base is equal to 0.0262. Kw is equal to H plus times OH minus. So H plus, trying to calculate, is equal to Kw over OH minus, which is equal to 2.93 times 10 to the minus 15, divided by 0.0262, which is 1.118 times 10 to the minus 13, negative log to the base 10 of that, is equal to 12.95. Once our answer to 2 decimal places is 12.95. Part E. The calcium hydroxide solution was saturated. A student added 0.0131 moles of magnesium hydroxide to 1 decimeter cubed of water at 10 degrees and stirred the mixture until no more solid dissolved. Predict whether the pH of the magnesium hydroxide solution formed at 10 degrees is larger than, smaller than, or the same as the pH of calcium hydroxide, and explain your answer. So what we're looking at here is if the solution is saturated for calcium hydroxide, what we're thinking about is whether the calcium hydroxide is more or less soluble than magnesium hydroxide. So this is looking at our trend in solubility of the hydroxides as you go down the group in group 2. So if you go down the group, magnesium hydroxide is less soluble than calcium hydroxide. because solubility increases as you go down the group. So that means less hydroxide would be produced in solution. So the pH would be lower. It wouldn't be as alkaline. So we're just going to add that answer. Affect the pH of magnesium compared to calcium would be lower. In brackets, we just add less alkaline. So in this next question, we're looking at the pH of a 0.46 mole per decimetre cubed solution of potassium hydroxide, another strong base. So KOH is equal to the concentration of OH minus. It's fully dissociated in solution and 1:1. So 1 times 10 to the minus 14 is equal to 0.46 times by the hydrogen ion concentration. So H plus is equal to 1 times 10 to the minus 14 kW divided by 0.46. And that gives us 2.174 times 10 to the minus 14. And the negative log to the base 10 of that value is equal to 13.66. So that is answer B. So in this next question now, we're looking at a Born-Haber cycle for potassium oxide K2O. And we are firstly asked to complete the diagram by writing the formula, including state symbols of the appropriate species on each of the 3 blank lines. So the first one is going to be the enthalpy change of formation for K2O. So that's the formation from its elements. So we're not going to need, and it's in their standard states. So it's potassium metal is a solid in its standard state, and oxygen is a gas, and we need half of O2, which is a gas, and that will be our enthalpy change of formation. The next thing we're going to do as we go around our Born-Haber cycle is we have to convert that 2K solid into 2K plus gas. So the first step we're going to do is the atomization of potassium, and we're going to need to multiply that by 2 because there are 2 moles of it. Carry forward the half O2 gas. In the second step, we're going to have to do the enthalpy change of atomization of oxygen. And that's the enthalpy change where let me good. The enthalpy change where 1 mole of atoms is formed from the element in its standard state. And then the final one here, we've got 2 times the enthalpy change of ionisation for potassium. First ionisation energy, and we've got 2 moles worth of that. And that will get us to the top line. That's completed our cycle. And then we've got some enthalpy change data. Use the data in the table to calculate the enthalpy of lattice dissociation of potassium oxide K2O. So I need to fill in some values here, so I'm going to go backwards and forwards a little bit. The enthalpy of formation of potassium oxide is minus 362. In fact, I might just pick a different colour so it stands out. So that's minus 362. And then we've got the atomisation energy. Enthalpy of atomisation of potassium is plus 90. And we need 2 of those. And then the next one we need is the enthalpy of atomisation of oxygen, which is plus 248. We just need 1 of those. And then we've got the first ionisation energy of potassium, and we've got 2 of those, it's plus 418. And we need 2 of those. And then the next one is the first electron affinity of oxygen, which is minus 142. And we just need 1 of those. So it's 1 oxygen going to an O minus. And then we've got the second electron affinity for oxygen, which is plus 844. And we're going to use all of these to calculate the missing one, which is this one here, which is the enthalpy of lattice dissociation. So we're going to go from here round in the opposite direction, so that way around the cycle. So we're going to go first of all so we're going to go opposite to that one, so it's going to be plus 362, and it's going to be in the same direction, plus 90 times 2, and in the same direction, plus 248, and then in the same direction again, plus 418 times 2, and then in the same direction again, minus 142, and in the same direction again, 844. Let's add all that together. Plus 362. Plus 180. Plus 248. Plus 836. Minus 142. So the answer I get is plus 2328 kilojoules per mole. 0.2328 kilojoules per mole. See calculation on BH cycle above, just for the avoidance of doubt. I don't want to have to write out the calculation again below there, so that's the calculation on the Born-Haber cycle. It's the one we've used. Part B then, explain why the enthalpy of lattice dissociation of potassium oxide, K2O, is less endothermic than that of sodium oxide, Na2O. Okay, so endothermic means how positive it is. So we're saying that the enthalpy of lattice dissociation of potassium oxide is a smaller value plus something smaller than that of sodium oxide, so that it takes more energy to break apart the lattice of sodium oxide than it does to break apart the lattice of potassium oxide. Okay, so it takes more energy to break the electrostatic forces of attraction between the Na plus ions and O2 minus ions than it takes to break the electrostatic forces of attraction between K plus ions and O2 minus ions. And this is because sodium, which is higher up in group 1, is a smaller ion than potassium, which is further down in group 1. This is because Na plus is a smaller ion than K plus, so the attraction is stronger between Na plus and O2 minus than K plus and O2 minus. So let's take a look at question 15. The value for enthalpy of solution can be determined in two ways: from a cycle using lattice enthalpy and enthalpies of hydration, and from the results of a calorimetry experiment. So I'm going to start by defining the term enthalpy of lattice dissociation. So this is the enthalpy change when 1 mole of a solid ionic compound is dissociated fully into gaseous ions. So looking at part B then, the enthalpy of solution for ammonium nitrate is the enthalpy change for the reaction shown. So we can see the enthalpy change of solution there is plus 26 kilojoules per mole, and we've got to use a suitably labelled cycle to calculate the enthalpy of lattice dissociation for ammonium nitrate. So let's construct this. So I'm going to start with gaseous ions. and I'm going to end with the solid ammonium nitrate. Dissolving that is plus 26, so that's going to be just up here. NH4 aqueous plus NO3 minus aqueous. And then we're going to hydrate dot my arrow back to front. Enthalpy change of hydration is the NH4 plus gaseous down to aqueous, and then this one is the NO3 minus gaseous to NO3 minus aqueous. So that is minus 314, that is minus 307, and this is plus 26. This is the one we want. That's the unknown. So we're going to start here, and we're going to go in the same direction as that, so it's plus 26. I'm going to go opposite to that one, so it's minus 307, and then opposite to that one, so it's minus 314. So plus 26 plus 307 plus 314. And so the answer to that is plus 647. So the enthalpy of lattice dissociation must equal 647 kilojoules per mole. A student does an experiment to determine a value for the enthalpy of solution for ammonium nitrate. The student uses this method. So they're measuring 25 centimetres cubed of distilled water in a measuring cylinder, pouring it into a beaker, recording its temperature, adding 4 grams of solid ammonium nitrate, stirring it and showing the lowest temperature reached. So we're calculating the enthalpy of solution for ammonium nitrate in this experiment. So Q equals MC delta T. So the mass of water is 25 grams, specific heat capacity 4.18, and the change in temperature is 20.2 minus 12.2. So we have 25 times 4.18 times by 8, which equals 836 joules of energy that's given out. Then we need to work out the number of moles of ammonium nitrate that have given that amount of energy out when they're dissolved. So that's 4 grams divided by the MR of ammonium nitrate, which is 80, which is 0.05 moles. So the enthalpy change of solution is equal to 836 joules per 0.05 moles, which is 16,720. It's endothermic because it got colder. So it's plus 16.72 kilojoules per mole. the uncertainty in each of the temperature readings from the thermometer is plus or minus 0.1. So we have to use 2 temperature readings, and we've got a temperature difference of 8 degrees. So it's 0.1 times by 2 for each reading, the start and the finish, divided by the measurement, which is 8, multiplied by 100 because we want a percentage uncertainty, and that equals 2.5%. Suggest a change to the student's method using the same apparatus that would reduce the percentage uncertainty. If we look at that calculation, the only thing we can change that would reduce the percentage uncertainty is the value 8. If that was a bigger number, then that would give us a lower percentage uncertainty. So the reason for the change is we need a higher temperature change. So we need a larger temperature change. So dissolving a greater mass of solid would lower the temperature even more. So the change is measure a higher amount of ammonium nitrate to dissolve in the water. Another student obtained a value of plus 15 kilojoules per mole using the same method. Suggest the main reasons for the difference between this experimental value and the correct value. Well, this is a reaction which is getting colder. So one of the possible solutions is that the heat gain from the surroundings has reduced the temperature change. That's a possibility, and that would have not permitted the correct change in temperature to have been recorded. In addition to that, the solid might not have completely dissolved. And this would also have reduced the temperature change. Okay, we've got some entropy data now for this part of the question. And it's asking us to calculate a value for the Gibbs free energy for the reaction, and we've been given delta H and we're given some entropy values. So we're going to calculate delta S for the reaction, which is equal to the sum of the entropies of the products, take away the sum of the entropies of the reactants. So it's equal to plus 146 plus 113 minus 151. which is 108 joules per Kelvin per mole. And now we can use delta G equals delta H minus T delta S. Delta H is plus 26, and it's in kilojoules per mole, so let's make that 26,000 minus 298 times by 108 plus 26,000 minus 298 times by 108, 32,184. So 26,000 minus 32,184, and that gives an answer of minus 6.184 kilojoules per mole. That was minus 6,184 joules per mole. And delta G is negative, indicating the reaction is feasible at this temperature. So a final calculation now. Ammonium nitrate decomposes as shown. We've got the entropy change, calculate the temperature at which this reaction becomes feasible. So delta G equals delta H minus T delta S. It becomes feasible when delta G is 0. And so rearranging that, delta H must equal T delta S, and therefore T must equal delta H over delta S when the reaction is feasible, which is plus 123 times 10 to the 3 joules per mole divided by plus 144. So 123 times 10 to the 3 divided by 144 makes a temperature of 854 Kelvin. Okay, looking at question 16. The element in group 2 can be used to show trends in properties down a group in the periodic table. State the trend in atomic radius down group 2 from magnesium to barium and give a reason for this trend. Okay, so the trend as you go down group 2 is for the atomic radius to increase. And the reason for that is that each element down the group has additional electron shells which repel each other. Okay, part B, state and explain the trend in melting point of the elements going down group 2 from magnesium to barium. So the trend melting point decreases as you go down the group. And the reason for that is that the metallic bonds are weaker. And the reason for that is because the metal ions are larger. So there is a weaker force of attraction between the nucleus and the delocalized electrons. More trends in part C. State the trend in reactivity with water of the elements going down group 2 from magnesium to barium. Write an equation for the reaction of magnesium with steam and an equation for the reaction of strontium with water. Okay, so the trend as we go down the group is for increasing reactivity with water. Increases as you go down group 2. And so magnesium with steam magnesium, apologies, magnesium oxide, magnesium and steam, which is H2 as a gas. So when you make when you do a reaction of magnesium with steam, instead of getting magnesium hydroxide, which you would get if you reacted magnesium with water, instead you get magnesium oxide, which is what was on my mind as I started to write the equation, magnesium oxide plus hydrogen gas, which you can light at the end of the, often this is done in like a boiling tube. You put a coil of magnesium into the boiling tube. I'll draw a little sketch of it. So often you would have like a piece of cotton wool here soaked in water, and then further up the boiling tube you'd have a coil of magnesium, and then you'd have a stopper in that and a little glass tube. And the little glass tube where you could produce the hydrogen gas, you can set fire to that flame so it'll burn. You can see the red flame that you get with hydrogen. That's the magnesium ribbon. And you get the white deposit of magnesium oxide left behind. By contrast, the equation for strontium with water. And this is with water liquid, will form strontium hydroxide, which is SrOH2 plus hydrogen gas. And we just need to balance this now, so the number of waters that's needed to make strontium hydroxide is 2, and that will balance that equation correctly. Okay, part D, sulfates of the group 2 elements from magnesium to barium have different solubilities. Give the formula of the least soluble of these sulfates and state one use that depends on the insolubility of this sulfate. And so the formula of the least soluble sulfate is barium sulfate, and it's used as a barium meal, given to make soft tissue appear visible on an X-ray. An example of soft tissue might be the digestive system. And that to assist with diagnosis. And it's really important that barium is insoluble in the form that it is ingested. So barium sulfate is very insoluble, and that means that although barium is quite toxic, because it doesn't dissolve in the bloodstream, it doesn't cause harm. If you used barium hydroxide, for example, which is very soluble, that would be very toxic to the patient. Question 17. M is a group 2 metal that forms the nitrate MnO32. A 0.320 grams of magnesium of M nitrate is heated strongly and decomposes completely. And then it's given us an equation for that. The mixture of gases formed has a volume of 225 centimeters cubed at 450 degrees C and 101,000 pascals. Determine the MR of MnO32 and therefore identify M. Okay, so we need to first of all work out, using PV equals nRT, the number of moles of gas that have been formed. So the gas has a volume of 225 centimeters cubed at 450 degrees C and 101,000 kilopascals, 101 kilopascals. So let's have a look. PV equals nRT. And so N is equal to PV over RT, which is equal to 101,000. And then we need to convert the volume into meters cubed. So that's, we're going to divide from centimeters cubed, we're going to divide by 1,000,000 to get to meters cubed. So it's 225 times 10 to the minus 6 in meters cubed. And then we're going to divide by the gas constant, 8.31, and then multiply by the temperature, which must be in Kelvin. So that's 450 plus 273. So our expression is going to be 101,000 times 225 times 10 to the minus 6 divided by 8.31 multiplied by 723. And so we get a value of 3.782 times 10 to the minus 3 moles. That's the amount of gas formed. And so that means the number of moles of solid that we started with can be related to the number of moles of gas that's been formed, because the number of moles of gas formed is 5 to 2 moles of solid. Okay, so to convert this to the number of moles of solid that we started with, we need to divide 3.782 times 10 to the minus 3 by 5 and multiply it by 2. In other words, multiply by 2/5. That's going to give us the number of moles of solid that we started with, which is 1.513 times 10 to the minus 3. And we know how much mass we started with. And so the MR is equal to the mass divided by the number of moles, which is 0.320 grams, divided by 1.513 times 10 to the minus 3. Which gives us 211.51, and that's the MR of our M nitrate. And then to calculate the value of M, we need to subtract the mass of 2 nitrates. So 2 lots of nitrate is NO3. Let's do the calculation there. 2 lots of nitrogen plus 6 lots of oxygen. That gives me 124. So the so that's 211.5 minus 124. And that gives me 87.5. And when we have a look at the periodic table, we can see that that is closest to the MR of strontium. So the identity of M must be strontium. Okay, so the final question, we have an electrochemistry question. Lithium ion cells are used to power cameras and mobile phones. A simplified representation of a cell is shown below. So we've got the conventional cell representation here. The reagents in a cell are absorbed onto powdered graphite that acts as a support medium. The support medium allows the ions to react in the absence of a solvent such as water. The half equation for the reaction at the positive electrode can be represented as follows. And so that reaction that's taking place there at the positive electrode is the reduction. Identify the element that undergoes a change in oxidation state at the positive electrode and deduce the oxidation states of the elements. So if you have a look at the equation, lithium is in its +1 oxidation state at both sides. And then the cobalt, oxygen is always -2 unless it's bonded to fluorine. So you've got 2 oxygens at -2 on the left hand side. So that's -4, meaning the cobalt is +4 on the left hand side. And on the right hand side, the oxygens are -4, but there's a negative charge overall, meaning the cobalt is in its +3 oxidation state. So the element that changes oxidation state is cobalt. Oxidation state 1, which is on the left hand side, is +4, and oxidation state 2 on the right hand side is +3. So the cobalt has been reduced. And then the next question asks us to write a half equation for the reaction which takes place at the negative electrode during the operation of the lithium ion cell. So hopefully, if you have a look at the negative electrode, it's this half of the cell here. So that's the negative electrode. That's where oxidation takes place. And we can see that the lithium is oxidized to lithium plus. So Li goes to Li plus E minus at the negative. Don't put any state symbols in there because, as it tells us, the support medium allows the ions to react in the absence of a solvent. So don't be tempted to put aqueous or solid. Just leave the state symbols absent here. Suggest 2 properties of platinum that make it suitable for use as an external electrical contact in the cell. So if you have a look at the cell reaction again, you can see that there is a platinum electrode as part of the positive electrode, part of the positive part of the cell. This, I'm just illustrating it in red here. So there is a platinum electrode. Platinum electrodes are used because they are unreactive and they are also electrical conductors. Suggest one reason why water is not used as a solvent in this cell. So if we have a look at the species which are present, hopefully you will notice that lithium, which is a group 1 metal, so it's highly reactive with water, which would form lithium hydroxide and prevent the cell from continuing to be chargeable and dischargeable. So lithium reacts with water to form lithium hydroxide, which would prevent the cell from recharging. And so that would cause our battery to cease to function as it should if there was water present in the cell. Part B then. The half equations for 2 electrodes used to make an electrochemical cell are shown. Write the conventional representation for the cell using platinum contacts. So if we have a look at these 2 cells, then the reduction, which is going to go on the right hand side, is the more positive, and the oxidation is the more negative of the 2. So this is the reduction, and this is the positive electrode. and this is going on the right hand side. This one is the oxidation. It is the negative electrode, and it is going on the left hand side. So we're going to start on the left hand side with our electrode. Now if we have a look at this, these are all species that are in aqueous solution, so we're going to need a metallic electrode that's not reactive. So we've already discussed one of those today, and that is platinum. So we're going to use platinum electrode, and that's going to be in the solid state, so we need a phase boundary. And then we need the two species, and the reaction is going to go from right to left, and so we need to put in our SO3, 2-, aqueous, SO4, 2-, aqueous, before we have our phase boundary. And then our reduction, which is on the right hand side, is going to go from left to right, so we need our ClO3- aqueous going to our Cl- aqueous, and again we're going to need a platinum contact as it tells us in the question. So that's our conventional cell representation. Next we need to write an overall equation for the cell reaction and identify the oxidizing and reducing agents. Okay, so the oxidizing agent, let's do that first, is on the left hand side of the most positive cell. So the oxidizing agent is going to be ClO3- in acidic solution. In the absence of acidic solution, it might have, well, it definitely will have a different standard electrode potential and different products. So I would always express the species, and then if it's inacidic, I would mention that too. The reducing agent is on the right hand side of the equation that has the more negative electrode potential, and so in this case that is the SO3 2-. That would be the reducing agent. So the overall equation then, so we're going to have the more positive one going forward, so it's going to be the sum of ClO3- plus 6H plus 6E- goes to Cl- plus 3H2O, and then we're going to add that to the reverse of the more negative equation, and we're going to need to multiply that by 3, so we transfer 6 electrons in both cases. So writing that underneath, we're going to have 3SO3 2- plus 3H2O goes to 3SO4 2- plus 6H plus 6E-, and now we can cancel the things that appear on both sides. So starting with the electrons, need to cancel. We've actually got 6H pluses on both sides, and we've got 3 waters on each side. So we can write the overall equation underneath, which I'm going to write in red to make it stand out, which is going to be ClO3- aqueous plus 3SO3 2- aqueous goes to Cl- aqueous plus 3SO4 2- aqueous, and that's our overall equation. And that's it for a bumper set of questions. So well done if you've managed to follow all of that. And good luck with your paper 1.